Hi, my name is Ari, and today I'd like to share with you our work on eye-tracking multimodal inference. How do people infer what happened in the past from visual and auditory evidence? We explore this question in the Plinko task. Participants see stimuli like this one and judge which hole they think the ball fell in. We have two conditions, a visual condition where participants only see the end state of the drop, and an audiovisual condition where participants hear the drop as it takes place. Participants then see the visual stimulus and judge which hole they think it fell from, combining these two sources of evidence. We collect three types of data in this task: participant judgments of the most likely hole, response times, and eye tracking data. We designed a model that emulates people's thinking in this task by running noisy simulations in an intuitive physics engine. The results of these simulations are weighted according to their distance from the observed location of the ball in the actual world. This allows us to compute a posterior distribution over holes and predict participant judgments. Our model emulates the process of human inference in this domain by engaging in an intelligent, resource-efficient simulation strategy. The model's utility function incentivizes it to run accurate simulations and simulations that help it resolve uncertainty. We initialize the model with a bias towards expecting the ball will fall directly under the holes. When choosing the first sample, the uncertainty for all the holes is the same, so it tends to start with the hole closest to the ball, in this case, hole 3. With each simulation, the model updates its uncertainty of where the ball would land if it was dropped in the given hole. The uncertainty term in the utility function incentivizes the model to try out different holes and see if they would end up giving it more reward. The model continues to sample until the expected reward for any hole surpasses a given threshold. We also use the model to predict the distribution of participant eye movements. We draw a heat map on the paths that the model samples, reflecting people's tendency to look at the paths they want to simulate to resolve uncertainty. We also add object looks, reflecting people's bias towards focusing on objects. Our model does a good job predicting participant judgments, explaining most of the variance in both the visual-only condition and the visual and auditory condition. The number of samples that the model runs also predicts participant reaction times. Our bandit model outperforms a regression baseline, which predicts the trial reaction time from the horizontal distance from the ball to the closest hole. Qualitatively, our model also does a good job of capturing the patterns of participant eye movement. Going forward, we'd like to formalize this comparison and better understand the distance between our bandit's predictions and participants' distribution of eye movement. Summing up, in this project, we implemented a multi-armed bandit model, which predicts participant judgments, response times, and eye movements. Going forward, we'd like to further investigate how auditory evidence influences participant response times and eye movements. We'd also like to understand how participants utilize visual attention to reduce their perceptual and dynamic uncertainty. Thanks.